Okay, looks like things have settled. So let's begin. Welcome to today's COMSOC seminar. We'll have, as usual, two speakers, Zsuzsanna and Evi. The format is as usual, so we'll have 20-minute talks followed by 10 minutes of questions. If you have a question during the talk, then please post it in the chat by writing question in capital letters, followed by your question, and we will discuss it after the talk. Our first speaker is Zsuzsanna, who will talk about cake cutting. So please
yes.
start.
Okay, I share my screen. No. Good?
Yeah.
Okay. And so, hello, everybody. So I would like to talk about strongly proportional cake cutting. So it's a social choice seminar. So all of you already know cake cutting, I think. And so it's a joint work with Attila Jó, Erel Szegál Halevi, and Shaun Man Yuan, and two of them are here in this call, so they can add comments. And so now how do I? Sorry. So I messed up my slides. So it's a usual thing. So you have a cake or a land or something, and you usually allow only parallel cuts. So that's why instead of a circular cake, we think of a 0-1 interval and cut at some points at the 0-1 interval. And this is the how we define the pieces. So there are n players. This time there are a finite amount of players, and each of them has pieces, and they all have their own utility function on it, and everybody cares about their own utility function. And this time there are no cherries. Cherries would be 1 point where the utility is big, but now we are dealing with the continuous type of cake. So in the continuous cake, there are no cherries. If you have a 1 point, that's worth 0 for everybody. That makes life easier. And yes, so we will want proportionality. If everybody wants the same demands, 1/n, then proportionality means everybody gets at least 1/n. And there was a famous algorithm by Banach-Knaster that was the last diminisher algorithm. We will just use this well-known algorithm as a motivation for our cake cutting story. That in this algorithm, one person started with a slice that is worth 1/n for the first player, then passes it to the second player. If it's good, now if it's worth more, then the second player diminishes, pass it on the third player, and the last person who diminishes, which means decreases the slice, that would get this given slice. And then that one player is already happy, that one player goes home, and we continue the rest with the remaining n-1 players. That's a very, very nice algorithm, easy to run, and also the last diminisher algorithm always gives me a proportional allocation that is connected. So that's very good for all of the players, but this time we want to have a strong proportionality, and we define strong proportionality in a way that something is strongly proportional if everybody gets strictly more than 1/n. So yeah, all of the players should have strictly more than 1/n. And what we got in the original last diminisher algorithm was connected, was proportional, but was not strongly proportional. So we want something that is strongly proportional and connected at the same time. And we realize that it's not always doable. But then the next question is, okay, but then what are the necessary and sufficient condition to make this strongly proportional cake cutting? And one thing that we can notice that clearly, if everybody has exactly the same valuations of the cake, then whatever you do, it can only be normally proportional. It cannot be strongly proportional because everyone has the same valuation. But there is a nice theorem from 61 that if you have anything else, so even if two player has something just a little bit different valuations somewhere in the cake, then that already gives us a way to make a strongly proportional allocation, so it exists. But of course, from this theorem, it could be anything in this small difference in the cake. So those slices are not necessarily connected. So this theorem alone doesn't help me with finding strongly proportional and connected allocations. So we started thinking, I think, yeah, RL wrote us an email and he has this question about strongly proportional connected cakes. And okay, what do we, yes. In this case, we will talk about queries that are also, I think, usual in cake cutting, that you can have the evaluation query, which means that you have a piece of cake and it returns the evaluation for agent I, or you can have a mark query that you put in a part of the cake and you put in a value R or R, how do you say it? And it marks the point where I should cut it so that agent I gets a value R from this part. And this time we claim that this mark function will return the rightmost point such that its value is R. Why is it important? Because we allow that sometimes a part of a cake is worth 0 for some of the agents. So if there is an interval here that is worth 0, then this algorithm, no, this query, this marking query might give me the leftmost endpoint of this 0 interval or the rightmost endpoint of this 0 interval, and it will actually matter a lot which endpoint do we get. And okay, so first, hungry agents. Hungry agents are those ones where there is no zeros in the evaluations. So for any time you give us a non-zero part of the cake, then they have non-zero utility. That's the easiest version inside our paper. And if we have hungry agents, then everything will be very beautiful. So we only care about the R marks. Okay, so the marks, and even out of those marks, we only care about this 1/n parts. So every agent marks in the cake which points are like, this part is worth 1/n to me, then the next slice that is worth 1/n to me, and the next slice that is worth 1/n to me, and the next slice. So each agent makes n-1 marks on the cake, and we compare only those 1/n marks. And this will be our sufficient and necessary condition that if and only if there are two distinct agents where the R marks, the special R marks differ somewhere, at least one place they differ, then we can already create a strongly proportional allocation. So that's a very nice condition. We only care about this 1/n marks. But if you have not hungry agents, then the problem becomes more complicated. So yeah, and okay, one more slide, sorry. So with this condition for hungry agents, you only need to check these n-1 points for any agent. So in total, it's n times n-1 queries. This is the upper bound, and we also had the lower bound, but whatever you do, at least you need half of it. So you need at least n times n-1 divided by 2 queries. Okay, but next move to the general agents. General agents can have places of the cake which is worth 0 of them, and it makes everything more complicated, because now I don't have a cutting point on 1/n value, but a cutting interval. So like for Alice, now Alice has very long 1/3 intervals. So all this part, maybe it's visible if I would point it in my slide. And also it's another very long 0 interval for Alice. But for Bob and Hannah, it's easier because they only have exact cutting points. And if we would just use our original condition for hungry agents, then we would be happy, because clearly Bob and Hannah has different cutting points. So we already have 2 agents with different cutting points, but sadly, it's not enough this time. I tell you that in this example 1, there is no strongly connected allocations. Why not? Because Alice should have strictly more than 40. And if Alice gets strictly more than 40 and it's connected, then she should get all of these zeros and part of this 40. Or if she gets the other part, then maybe she should get this endpoint of 40, all of these zeros and part of the middle 40. Or, okay, the third case would be for middle one plus some of this and some of this. That would be even worse for the other 2 players. So whatever we do for Alice, the remaining part for the other 2 players are not doable anymore. So if like Bob and Hannah gets this thing, then Bob should need like this part, but strictly a little bit bigger, epsilon bigger, because it's strongly proportional, but then it's not enough left for the 3rd player. So whatever we do, we cannot do it. So this was our counter example, but imagine that we have this new allocation. This time this is doable. Now Bob's utility function changed, and this time it's doable because we can give a lot of 240s to Alice. Alice is very happy. Bob gets this part and half of this interval with 38, and Hannah gets this 40 plus half of this interval. So also very good. So everybody is happy and all the pieces are connected. The one thing that we want to mention here is that the cutting points, or 1/3 points and 1/3 intervals, are exactly the same in example 1 and example 2. So just by looking at the placement of these T/n marks, it will not help us, because that's not enough information to decide. For non-hungry agent, we had a separate sufficient condition and a separate necessary condition, and they are not the same, but we can put them closer. So necessary condition this time was that there are 2 agents where, sorry, I don't see. There are 2 distinct agents such that the interval of those 2 agents are disjoint. This is a necessary condition, and the sufficient condition would be even stronger, that these R marks, so 1 over n marks for all agents are pairwise disjoint. And if you have exactly 2 agents, then the story is nicer, because then these 2 conditions coincide, and then you will have that strongly proportional allocation exists if and only if the intervals, these 1/2 mark intervals, are disjoint. Again, you know that they are not hungry, so it can be that both of them are not just point but interval, but these 2 intervals are disjoints, then it's doable. If those 2 intervals are not in disjoints, then clearly we cannot find a strongly proportional solution. And so what else we can do is, instead of just looking at these marking points, run an algorithm, but this algorithm will be a very, very big running time. This time it will be n factorial. And if you're okay with n factorial running time, then what you can do is that look all of the permutations. And for given permutations, every agent starts marking the cake. So first, the agent 1 marks it at value 1 over n, but at the rightmost point, that is 1 over n. Then the second agent also marks it at the rightmost point that is good for her, and so on and so on. And here we will end up at some point, we call it mark sigma, where sigma is the permutation, so it depends on the permutation. And we claim that if this marking point for sigma is less than 1, then we have a good allocation and we can give strongly proportional allocation for everybody. But if we would go over 1, then not everybody can get the slice that they want, so it doesn't work. So with this marking algorithm, it gives us a sufficient and necessary condition that we wanted, but at the cost of a very big running time. And what can we do? Something that we can do, okay, this is my original, that it uses n times n factorial queries. What we can do is we can improve it a little bit. I don't tell you the algorithm, but this algorithm is like similar to dynamic programming, that you keep in mind some of the queries. And this is an improved upper bound that is just n times 2 to the n queries, but still 2 to the n is still exponential, even though it's much less than n factorial. So we should still improve this this number of queries. And should I look at the chat? Maybe later. Okay. And I think I will finish soon. So what I want you to say that we have these results so far, but it's still ongoing work. So we still want to reduce the number of queries to hopefully a polynomial algorithm. That would be very nice. We don't know if it's doable or not. Also, we have some results about unequal entitlements. So in the case where agents have an unequal entitlements, of course, there is not always a connected strongly proportional scale cutting, but we can have some partial results. And an interesting future work could be that chore cutting, which means that you don't have cakes which are good for you, but chores that are negative value, then how could we share it between the agents? Okay, and thank you. Thank you very much. Thank you for your attention.
Thanks for the nice talk. Let's give a round of applause.
Yes. Should I look at the questions or?
So I can have a look. So Dominic had some questions, but it seemed like those were answered by Eric with a clarified otherwise.
Yes.
That's good. Right. Then, so Nisak, do you want to read out your question yourself?
Sure. Great talk, by the way. So I was just kind of wondering that is strictly greater than 1 over n is interesting to know, but in practice, kind of this is not any, any better guarantee than 1 over n, right? I mean, it doesn't tell you how much more than 1 over n. So I was wondering if how these results can be strengthened to identify conditions when egalitarian welfare greater than equal to some alpha can be achieved, parametric guarantees in terms of alpha.
So alpha is a given number over 1 over n.
Given number between 1 over n and 1 can be by some necessary or sufficient conditions when we can get egalitarian welfare alpha.
Yeah, we can run this algorithm with n factorial times, but yeah, I don't know, but it's good. I will think about it.
The algorithm that you described, it checks all permutations, should also answer this question. You just put in the alpha as a parameter.
Yes.
Okay. Yes, but it runs in exponential time.
Right, but it will find it when it exists, and I guess one question is, can we find some conditions on the valuations for which we can say whenever the valuation satisfies this condition, such a allocation would always exist.
Yes.
Yeah. I have another question. I don't see any other questions, so I may as well just stay unmuted and ask it. What about strongly envy free?
It's a future work.
Do we know anything without connectedness? I am not up to date on my
connectedness. Oof. Era, do you know something?
There is a nice condition called super envy free, which means that you get more than 1 over n and all others get less than 1 over n, which is the best you can hope for. And there is a necessary and sufficient condition related to a linear independence of the valuations, something like this. It's very cool, but of course not connected at all. We have no idea how to make it connected.
Perfect, thank you.
But Stromquist also asked the same question. It's probably a good one.
So connectedness makes an assumption about the underlying topology. So in this case, that it's like that you have an interval. Do you also consider other topologies? So maybe 2 dimensions or whatever.
Maybe consider a cycle like this. Then I don't know.
One interesting case is simply to identify the 2 endpoints of the cake.
Yeah.
Then you have a pie. And then we don't, it's interesting, it's a very small change, but we don't know what happens because now we don't have, so of course we can pick a point at random and cut from it, but it's not necessarily, it is not necessarily a condition anymore, even for hungry agents. Because you can cut from infinitely many places. So even this case is challenging.
Any more questions?
Yes, I put a question in the chat. What about using the fact that the cake is round in the sense that you can orient the direction of your parallel lines over an interval of 2 pi? If you look at this set of cutting points, it will presumably, in the case of hungry agents, change continuously and exhibit all kind of interesting exchange points. And can you use that?
So maybe you just mean that round is like we go back to this pi version where they are unconnected, or you mean that we can do any type of cutting in a circle?
No, I mean that you can choose the direction of the parallel line.
Ah, directions. Ah, it's a good one. Yeah. I just put the parallel lines on the slide because that was the
You wanted to reduce it to a one-dimensional problem, but if you take the two-dimensional series, I think the problem becomes far more complicated.
Yeah.
Thanks.
More questions? So on your last slide, you had thanks for your attention in 3 languages, and one of them was German, and I was wondering why it appeared there.
Yeah, because you wrote me an email, and I thought that it's like University of Bonn, so I should put Danke für die Aufmerksamkeit, but then I realized it's International COMSOC conference, but yeah, I think it's not a problem if I put it there.
Okay. So then we'll have our coffee break. Dominic, will you send us to breakout rooms? Okay, great. So then we will resume with the next talk in 10 minutes. So enjoy the coffee break. Okay, welcome back. So now we'll have our second talk by Evi. Could you start sharing your screen, please?
Sure.
So Evi will talk about citizens' assemblies. The screen is yours.
Okay, thank you very much. All right, so today I will talk about fair representative citizen assemblies. I will mainly focus on joint work with Suru Sebatian, who believes is in this talk, so probably in the meantime he can reply some of your questions. And also I will towards the end, I will also talk about some recent results from a joint project with Yannis Karagiannis and Yannick Peters. And I think Yannick is also here, so he probably will also be able to answer some of the questions. All right, so let's get started and let me introduce the idea of citizen assemblies for those that are not familiar with this. So in modern representative democracy, the idea is that every couple of years we select our representatives, or every few years we select our representatives, and after that we are not involved in any decision making. And this is something that different cities or countries around the world want to chase, and so they want to increase civic participation. And an idea for increasing civic participation is to do this through citizen assemblies, where the idea of citizen assemblies is that given a population, given citizens of a city, let's say, we select a panel at random, on some way from this population, and then this panel is in charge of deliberating and making recommendations for a particular topic at hand. And then the authorities of the city or of the country should take into account the recommendations that the panel made. So this is actually quite old idea, and the last decade, I think, has revival again and is used around the world, either in a city level or even in a country level. For example, Belgium very recently established a permanent citizen assembly for climate change. So it is an idea that is adopted by many different authorities around the world. And in this talk today, I'm going to focus more on the process of selecting a panel at random from the given population, a process that is known as sortition. So the easiest way to apply sortition, and probably the more traditional way to apply sortition, is given a population of size n, and given that we want to construct a panel of size k, we can select just k representatives of the population uniformly at random without doing anything smarter. So this is a very simple way to do that. And there are two main advantages of applying sortition this way. The first advantage is that everyone has equal chance of being selected. So in this case, everybody is selected in the panel with probability equal exactly k over n. And the second advantage is that in expectation, a panel that is selected uniformly at random will reflect the composition of the population. And so in this talk, I want mainly to focus more on the second property. And let me visualize what I think by what I mean by that. If we have a population that looks like this, where 1/5 of the people self-identify as non-binary, 2/5 are females, and 2/5 are males, when we get a panel uniformly at random, then in expectation, the panel will look like this. So in expectation, we will see that 1/5 of the representatives self-identify as non-binary, 2/5 are females, and 2/5 are males, which is nice, which is something that we want from the panel. However, it's not very difficult to imagine another uniform selection. We might see a panel that looks like this. So a panel that does not really reflect the composition of the population. So all the representatives, for example, are males. And this is something that is not desirable in practice. This is something that we don't want and practitioners do not want. And so different strategies are applied in practice to overcome this obstacle. And one idea is to, instead of doing uniform selection, to do stratified sampling. So stratified sampling means that we partition the individuals into disjoint groups, and then from each group, we pick representatives uniformly at random. For example, in this case where we have, we care for just one feature, which is the gender of each individual, we can partition the individuals into 3 disjoint groups according to their feature. And then from each group, we can select proportional representatives. For example, we see that the first group consists 1/5 of the population, and so we can select 1/5 of the representatives from this group uniformly at random. Similarly, we see that the second group consists 2/5 of the population, so we can select 2/5 of the representatives uniformly at random. And the same with respect to the last group. So here we see that at the end, we ensure that we have proportional representation of the population with respect to this feature. And we also ensure fairness because we see that the way that we got the representatives do not really affect the probability of someone being selected in the panel. So this is a nice approach. However, this idea breaks when we have more features and we want to ensure proportional representation over all the intersectional features. For example, if now in the population we care about both gender and both color, if we partition the individuals into disjoint groups according to all the different intersectional values that they can have with respect to their features, we see that now we have 6 groups and we have just 5 seats available in the panel. So there is no really way to get a representative from each group. Because essentially what I'm saying here is that when we have multiple features and when we care for intersectional representation, the number of groups can grow exponential. And so there is no really way to have at least one representative from each group. So a different idea that overcomes this immediate problem and in some sense is more general is instead of doing stratified sampling, to set quotas to different features, either in an individual level or in an intersectional level. And so this is something that practitioners actually do right now. And while in principle we can set quotas over intersectional feature, what people usually do in practice is that they focus on individual features and they set quotas with respect to individual features for a particular application at hand. For example, they set quotas with respect to gender, with a level of education, or with any other feature that might be related to a particular application. And so I'm going to show you that this approach also has some disadvantages. And actually, let's consider the following population, where we have a population that consists of 90 individuals, and each individual is characterized by 3 different features. So we have feature star, feature heart, and feature flower, and all these features are binary. And let's say that we want to create a panel that has a size 30. So we have 30 seats available in the panel. So what practitioners usually do in this case is that they focus on its individual feature and they try to set quotas to ensure a proportional representation of its feature to the panel. So let's do the same in this example. Let's focus on the first feature, which is feature star. We see that 1/3 1/3 of the population has star equal to 0, 2/3 of the population has star equal to 1. And so we can set the respective quotas, where we can ask 1/3 of the representatives to have star equal to 0, which means 10 representatives to have star equal to 0, and 2/3 of the representatives to have star equal to 1. Similarly, we can focus on the second individual feature, the feature heart, where we say 1/3 of the people have heart equal to 0, 2/3 of the people have heart equal to 1. And so we can again set the respective quotas, and similarly with respect to the last feature. Okay, so we have set all the quotas that we want to satisfy, and given these quotas, we will try to find a panel that satisfies these quotas. And so it's not very hard to see that this particular panel satisfies these quotas. For example, we see that we have just 10 people that have star equal to 0, which are the yellow people, and just 10 people that have heart equal to 0, which are the green people, and so on. So it is easy to verify that this panel satisfies all the quotas that we have set. However, as it's not very surprising, we see that this panel doesn't satisfy anything with respect to intersectional features. For example, we see that 1/3 of the population has all its features, all their features equal to 1, which are the gray people in the population, and we don't have any representative in the panel that is gray. So while this panel satisfies all the quotas that we have set over individual feature, doesn't seem to satisfy proportional representation in a more rigorous way. And so I think we can agree that the panel on the right is more proportionally representative, because we see that here 1/3 of the representatives are gray, as 1/3 of the population are gray individuals. So, okay, the question is, and what can we do? Stratified sampling doesn't work, setting quotas. If we want to set over individual features, we don't get any proportional representation over intersectional features. What could be an alternative? So in this work, I would like to introduce the idea of, given a population, instead of setting quotas, to try to build a representative metric space as a function of the quotas, and try to do something in this metric space. So this is an idea that was introduced in a previous paper in Europe's 2022, and it is something that an idea that we reuse in this particular work. And so the idea of, given a population, building a representative metric space is quite simple. So given the different features that we care about for a particular application, we can build a representative metric space as a function of these features. So for example, in this case that we care for 2 features, we can create a 2-dimensional metric space, and then we can place the individuals into the metric space as a function of their features. For example, here I see that the blue individual has a star equal to 0 and heart equal to 0, and so I place this individual at position 0, 0. So this is the tool that we are going to use in this work, and a reasonable question is, what do we gain by this? And before I define things more formally, I want to give an intuition regarding what we can gain by having a metric space rather than constructing quotas. So let's go to the previous example where we had these 90 individuals, and we cared about these features. When we construct a metric space as a function of these features, now it is quite clear that at position 1, 1, 1, we have 1/3 of the population. So it is quite clear that this region is cohesive, and so probably these individuals, this group of individuals in the population might deserve some representatives in the panel. And so if I hide the table of the population and I keep only the metric space and the quotas that we had before, from the metric space, it is quite clear that this region is cohesive and so deserves some representatives, while from the quotas, there was no way to conclude that 1/3 of the population has all their values equal to 1. So this is high level what we gain by having a metric space, but let's define how we will ask for proportional representation in a more rigorous way. And let's get a step back and let's ask what proportional representation intuitively means. What do we want to achieve through proportional representation? And I think we can agree that to some extent, proportional representation means that every group of individuals that forms X% of the population is eligible to select X% of the representatives. So any group of individuals that form X% of the population expect to have X% representatives, to have X% of the representatives in the panel. And so for those that are familiar with the idea of the core in committee selection, might not be too difficult to see the connection of this intuition with the idea of the core. And so actually in this work, we use the idea of the core for defining what means a panel to be proportional representative. And so we said that a given panel P is in the core or proportional representative if there is no a subset of the population that forms X% of the population, and another panel P prime that has X% of the representatives of the available seats for the representatives, such that all people in the subset Pareto improve by choosing this panel P prime rather than the initial panel P. So all of them feel somehow more represented by this panel P prime versus the initial panel P. And so here, because we are in a metric space, essentially we can measure how satisfied a person feels under a panel P versus under panel P by just finding the cost of this agent for a particular panel. And so for exactly measuring what is the cost of an agent for a particular panel, in this work we use the idea of the Q cost, where we're saying that the Q cost of an individual for a particular panel is equal to her distance from the QF closest panel member. So for Q equal 1, given a panel, a person cares about her distance from the closest person in the panel, and for Q equal K, a person cares about her distance from the furthest representative in the panel. And so we wanted to ensure that a panel is in the core if no subset of the population can find another panel where all of them are, another panel that is proportional to their size and all of them are happier. In general, a panel in the core under the Q cost is not guaranteed to exist. And so we saw the multiplicative approximation with respect to factor alpha, where alpha essentially measures how much someone can improve by deviating to a different panel. Okay, so this is how we defined in this work what proportional representation means and what we require from a selection algorithm to achieve. But at this point, I would like to remind you that the most important, or one of the most important properties of sortation and uniform selection is fairness, which means that it guarantees that each citizen has the same chance to be included in the panel. Everybody selected with the same probability. And so in this work, we wanted to keep this important property. So we wanted to keep fairness. And on top of that, we wanted to ensure proportional representation. So on top of that, we wanted to ensure that the selection algorithm returns a panel that is in the alpha core. And so because this algorithm is randomized, we said that the selection algorithm is in the exposed alpha core if every panel that returns is in the alpha core. And so the question is, can we really do that? And in this work, we said that, yes, we can do that. And there exists an efficient selection algorithm, which we call fair greedy capture, that first is fair. So it returns each individual with probability K over N, and also is in the exposed 5.71 Q core for all the values of Q. And so in this case, at this point, I want to clarify that our algorithm does not need to know Q, and for all Q concurrently, satisfies this property. So essentially, we're able to show that we can keep all the good properties of uniform selection, and on top of that, ensuring proportional representation exposed. Okay, so that was the result, the main result of the first work. And now, very briefly, I would like also to mention a new result from my recent work with Yanis and Yannick. So the question that we asked in this work was a bit different. And essentially, we asked that in the previous work, we saw that we can have a proportional representative panel always. But does a proportional representative panel, or does a panel in the core ensures that we reach a decision that is good for the whole population. So does this mean that the panel is able to find a solution that is close to what the whole population would make? And so for rigorously answering this question, we assume that in the metric space that we don't have only the individuals who now we can think them as the voters or the agents, but we also have the candidates or the alternatives or the different decisions that the panel can make. And so now you can think this metric space essentially as an ideological metric space, where each person has some idea of what is the optimal candidate for them, and also the candidates are in the metric space. And so for measuring how good the decision is for the whole population, we said that given a panel, the panel is able to find the best solution for them, where the best solution for them is means that the solution that minimizes the social cost for the panel. So the sum of the cost of all the individuals that are in the panel. And we wanted to compare this solution, this candidate, with respect to the candidate that is optimal for the whole population, which means the alternative that minimizes the social cost for the population and not for the panel. And so we wanted to see what approximation to the social cost for the whole population the green solution achieves versus the red solution, which is the optimal of the whole population. So in other words, we wanted to see in the worst case, given a particular algorithm, what is the expected social cost that we have from the optimal solution that is returned by a panel versus the social cost that we have of the optimal solution for the whole population. And we wanted to see in the worst case how large this ratio can be. And so not very surprisingly, we saw that uniform selection does not guarantee any reasonable approximation to this ratio, and so the approximation is at least omega n, while fair greedy capture guarantees a constant approximation. And so we see that fair greedy capture does not only guarantee proportional representation, but also guarantees that this panel can reach to a good decision for the whole population. And okay, at this point, I would like to mention that this concept is currently quite large, and there is an open question here how we can close this gap. But I think this is a quite promising result for fair greedy capture. Okay, and I would like to stop at this point. Thank you very much.
Okay, thank you very much. Let's give a round of applause. Okay, great. So I think in the chat there was there's one open question by Nisak.
Yeah, hi. Thanks for the great talk. So you talked about kind of your initial motivation came from this individual and intersectional kind of representation exposed, and then you kind of talked about building the metric out of the features that we care about, and then we talked about kind of the core with respect to this metric that we formed. And I was just kind of wondering, how well would you say, at least empirically, the score with respect to the metric that we built, how well that guarantee would translate back to the quota-based representation for individual and intersectional features? And since we have a flexibility of building the metric however we want based on the features, maybe we should be looking at the L2 or the L infinity or some weighted L1 or some other kind of metric. So is there something you can say about how to build the metric given the features?
Okay, thanks for this question. So in general, our algorithm does not guarantee anything about the individual features. And of course, this can be a problem in practice. But I think that the good thing is that essentially we can make the core requirement as a quota requirement, and then try to satisfy these quotas as much as possible. So what I mean by that is what essentially our algorithm does is that it partitions the whole space into different groups, and it ensures that this partition has a lot of each group in this partition has a lot of people from the population. And so essentially what we can do then is that given this partition that the algorithm has made, we can assign, we can think this as an extra feature for each individual. So essentially what our algorithm does in the metric space is that it creates some balls, and each individual is included to some ball, and it creates k balls. And so we can say that each individual belongs to a particular ball. And so this is an extra feature for this individual. So you can imagine this as colors, like we have a blue ball, green ball, red ball, and so on. So each individual belongs to a particular color and has a particular feature. And then we can ask as a quota now that from each ball, we want at least one representative. And so from we have, let's say, n over k people that are red in the population. So we want at least one red person in the panel. And so after doing this translation, essentially we can have all the quotas that we want in order to ensure the core. And then we can have quotas with respect to individual features or for whatever else we care about. And then we can say, we can run algorithms who have some experts in this called design for satisfying these quotas as much as possible. So essentially we can have core and individual representation over the features by doing this translation.
I see. So just to understand, just to make sure I've understood correctly, because you're saying that your algorithm, once it finds these balls, has the flexibility of choosing any individuals from each ball of that are of prescribed number. You can kind of do that selection while trying to maximize the representation in the original thing as much as possible.
Yes, yes,
exactly.
Thank you. Marcus, you have a question.
I have a couple of questions. One of them I think is actually pretty much a variation of Nizar's question, but I'll ask it anyways. So yeah, like Nizar, I'm interested in the fact that the algorithm seems to depend a lot on the metric, and there's a lot of arbitrary ingredients in the metric. The algorithm also depends upon the choice of cost function, right? You're using this Q cost function, but that's obviously just one of many possible cost functions we could use. You know, one can imagine some kind of like weighted average of different Q cost functions, and then you have a choice of like how you're going to weight the different Qs. One could imagine assigning costs some other way. So I'll just put both my questions out, and then you can answer them. So my first question is essentially, how do you have some idea how much the results depend upon the choice of metric and the choice of cost function? In other words, is there sort of a comparative statics thing where if you sort of say like, okay, we continuously move over a space of possible metrics where we sort of weight different features in different ways or whatever, you know, do we have some idea how the sort of solution that pops out varies as a function of that? Or does it vary? Because if it doesn't vary very much, you know, that's interesting, right? My second question is more of a clarification question. All the examples you looked at, the metric was defined by kind of categorical features, right? Like people are either like male, female, or non-binary. They fall into one of like, you know, X, Y, Z racial categories, whatever. But many of the characteristics that we might be interested in are not categorical, and they already come with some kind of a metric structure. So if you look at something like, say, age or education level or income level, right? Those are, you know, clearly demographically important characteristics of a person. Now, one of the advantages is all those things kind of like you can quantify them with a number. So there's already like a metric there for you to use. But then, of course, there's still the problem, how do you define a metric over the combined space of all those different characteristics, right? Effectively, like, you know, how do you trade off between age differences versus income differences versus geographical location versus categorical features like race or gender or whatever. So I guess my question to sort of close all that is your algorithm, does it only work for categorical features, or does it work for these for metrics defined, basically like any metric space, even if the metric is defined using some kind of numerical characteristics?
Okay, so we'll start with the last question. So our results depend only on the existence of a metric space.
Okay.
It has nothing to do with how we construct this metric space.
Great.
That
Okay.
said, if for a particular application, you create the metric space in a particular way, and you create another metric space with another way, then I'm not sure how similar the two solutions are. So I'm not sure how the partition of the two that we have from the two different metric space, how close are to each other. I can imagine that they can be arbitrarily far away. So you can imagine a completely different way now the metric space that we get a completely different solution. So I think indeed this is a problem in practice. So I'm not sure if this is our problem as computer scientists or this is a problem of practitioners, but we want to have a rigorous way to say that given this particular application, given these particular features, this is the optimal way to construct a metric space. And what is optimal, I don't know. I have no idea how to define it. So yes, I think it is important to somehow have a sense of how to define this metric space. For example, for your question for numerical versus categorical features, in our experiments, what we did is that given to individuals, we measure the distance with respect to individual features. So for example, for numerical, when we're talking about the rates, we just got difference in the rates. And when we're talking about categorical features, we just say, for example, if they are binary, like woman versus man, if it is the same, they have distance 0. If it's not the same, they have distance 1. And then we sum up over all the different distances. But also in our experiments, for example, in some cases we got the weighted version of this sum. In some other cases, they're not weighted. So there is indeed a lot of freedom of how you define the cost and how you build the metric space. And for example, the Q cost is one option which we believe has some particular advantages for the application of sortition versus, for example, the average distance. But again, someone can get a different approach. And now our results depend on our cost function. So we saw that this is true for Q cost. We don't show if this is true for any other function. So this is also an interesting open question. But I think the important message here is that as long as you have a metric space, probably you can satisfy a notion of proportional representation by using the idea of the core.
Okay, thank you very much.
More questions? So Judy had one question in the chat about fairness over time when you have repeated selection, but I think this has been answered already. Anything else? Yannick?
You know what would happen if you, let's say, personally have features you care much more about than others could care about? So, for instance, in Germany, we had like a citizens' assembly on nutrition. So maybe you care much more about somebody representing you by being vegan and you don't care about age or so at all. Then this would kind of destroy the metricness, right?
Yeah, not at all. I think this is a nice thing by having the freedom to design the metric space as you want for the particular application. For example, in the process that I described before, where for every two individuals, you get the difference with respect to individual features, and then you get the sum over them. For example, when you care about a particular feature, you can put much more weight in the difference between the difference for this particular feature. While you don't care for another feature, you can put quite lower weight with respect to that. So you can adjust the metric space in a way that exactly captures this idea that some features are more important versus some others.
Let's say you care very much about being vegan, and another person, let's say, cares very much about age. Then there's like an old vegan person, then the other old person would be close to the old vegan person. You would be close to the old vegan person, but if the other person is not vegan, you would be very far away. So that would kind of break the triangle inequality.
So essentially, you're saying that each individual has their own optimal metric space. Yeah. I see. Yeah, okay. In this case, if the metric space is not common, I think, yes, in this case, I don't think that our results hold.
Okay. So let's thank both of our speakers again. And then we finish with an announcement. So our next session will be on April 18, and our speakers will be Andrew Mackenzie and Wes Holiday. And we hope to see you there. Bye-bye.
Thank you.